Okay, so we're going to move our thinking from 2 dimensions to 3 dimensions. 2 dimensions, we have our Cartesian plane. We have 2 axes, the x and the y axes. 1 coordinate plane divides it up into 4 quadrants, and the first quadrant, second quadrant, third quadrant, fourth quadrant defined as we usually have them. So that's 2 dimensions. A single point on there can be represented by what we call an ordered pair. We now go to a Cartesian space rather than a plane, so it's now 3-dimensional. Notice the setup I have it. I've got x and y lying flat and z-axis coming through it. Now once you go into 3 dimensions, of course you can turn this and have it in any orientation you like. This is probably one of the more standard ways of doing it. There are now 3 axes, the x, the y and the z. 3 coordinate planes, so there's our xy that we're used to seeing, but there's now also a yz plane and an xz plane. But it'll divide it into 8 octants, set of quadrants. And there's all the definitions there for which quadrant is which. So the first 4 is when z's positive, the second 4 is when z's negative. A single point then is now defined by an ordered triple, and we name the coordinates logically x, y, z. So that's the order that we would go in. Now the problem is we're representing a 3-dimensional space on a piece of paper, and so drawing it like that, you really have no sense of where P is. So sometimes we find it easier to draw a rectangular prism, and so then you get a better feel for where P actually is in the space. Now in 2 dimensions, we know lines parallel to the coordinate axes. So parallel to the x-axis, y equals a constant, in this case 3. Parallel to the y-axis, x equals a constant, in this case 2. Now when we go to 3 dimensions, x equals a constant, y equals a constant, z equals a constant is no longer representing a line. It's now representing a plane. So planes parallel to that xy plane that I've got lying flat. So the one that goes through the point 231. So that would be z equals 1. Everywhere on that plane, the z value is 1. But other than that, it's the same as our regular number plane. If it was y equals a constant, that's the one that's going to be parallel to the xz plane. And that's y equals 3. If it's parallel to the to the yz plane, it's x equals 2. A couple of standard formulas that we use in coordinate geometry. Distance formula we know is square root of x2 minus x1 squared plus y2 minus y1 squared. So in 3 dimensions, I want to find the distance between these 2 points. Again, in order to visualize it, let's draw in a line, but I'll also put a prism there to give it some sort of space. So we're basically finding the diagonal of that rectangular prism. The height is the difference in the z values, isn't it? Now if I can find the length of the base, the diagonal on the base, we can use Pythagoras and get the length of PQ. So if I project that down to the xy plane, might make it easier. Because now it's just like normal coordinate geometry. It's on the xy plane. So I know the hypotenuse would be our 2-dimensional distance formula, the square root of x2 minus x1 squared, and so on. Well, therefore, the distance between PQ will be the square roots of the square root of x squared minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And all it really turns out is that. So it's basically the same formula, but now we're doing it for the other coordinates as well, the z difference in the z values as well. And that actually flows through to any dimensions. And I know it sounds weird when you start talking about 4 and 5 dimensions, the distance between 2 points, but that's, it would just flow through. So midpoint, 2 dimensions, we're used to seeing it like that, but the same idea, it just flows through. So in 3 dimensions, we just add in the 3rd coordinate, and it'll be the average of the z coordinates. You want to go to 4, 5, you keep going. Alright, so just a quick touch on it to begin with.